Okay, so this is section 12.6. We are going to be graphing polar equations. Okay, there are two very good ways for how to graph polar equations, and I'm going to show you both of those ways, and you get to decide for yourself which way you're going to use. Okay, so method number one is by plotting points. And this is my preferred method. I use this method just because I'm really bad at memorizing, and I would just prefer to plot points. And then the second method is by knowing some basic parent graphs and in general the types of curves that polar curves are going to look like, and then you can graph it based on what you know it's supposed to be. Okay, so I have two examples here. We're going to start with example number one, r equals 1 minus 2 cosine theta. And I'm going to show you these two examples by plotting points. Okay, so on this, I have our example number one, r equals 1 minus 2 cosine of theta. And to graph this, I'm going to make a t-table with values of theta and values of r. So I'm going to start, and I'm going to choose theta equals 0. So I'm here where theta is 0. Okay, at theta equals 0, r would equal 1 minus 2 cosine of 0. And the cosine of 0 is 1, and so this answer for r is negative 1. So at 0, I'm going to go backwards 1 and plot the point 0, negative 1. All right, now I'm going to choose my next theta. I'm going to go ahead and choose pi thirds. And the reason why I'm choosing pi thirds is because I know I'm going to plug pi thirds into cosine, and the cosine of pi thirds is a half. And so I'm going to get a nice pretty answer. I'm not going to try to plot any points with radicals in them, like a radical 3 over 2. I don't really want to do that, but 1/2 is okay, because this r would be 1 minus 2 times the cosine of pi thirds, which is a half. So 1 minus 1 minus 1 is 0. So at the angle 60 degrees, I get an r of 0. Interesting. I'm not quite sure what's happening between 0 and pi thirds, but let's keep going. Let's look at what happens at pi halves. So at 90 degrees, the cosine of 90 degrees is 0, and I have 1 minus 0, so that's 1. So at 90 degrees, I'm going to go up here and I'm going to do 1. Okay. Then let me try to connect these points a little bit and explain what's happening. So between 0 and pi thirds, that's pi thirds would have been here. Wait a minute. That's pi halves. Pi thirds would be here. Okay, so between 0 and pi thirds at all of these angles, the cosine of those angles was positive, but it was less than a half. And so what happens is that when I took 1 minus 2 cosine, I got these really, wait, was it less than a half? Hold on. Okay, the angles between 0 and pi thirds, the cosine of these angles between 0 and pi thirds is more than a half. And so I was taking 1 minus values that were less than, or that were more than a half. And so when I multiplied by 2, I got a number more than 1, but I got negative r's. So all of these gave me really small negative r's between the angle of 0 and pi thirds. And so this was my original point when theta was 0, and then I got 0 at theta equals pi halves. And now between pi thirds and pi halves, I'm going to get very small positive numbers. Okay, let's move on. Let's do 2 pi thirds. 2 pi thirds is also 60, but it's in the second quadrant where cosine is negative. And so I get 1 minus 2 times negative 1/2. So this is going to be 1 plus 1, or 2. So at 60 degrees, which is here, this is 2 pi thirds here, I have an r of 2. So I'm going to go out 2 from the origin and plot that point. Now I'm going to connect to there. Okay, let's continue on. Let's do theta equals pi. The cosine of pi is negative 1. So 1 minus 2 times negative 1 is 1 plus 2. I get my highest value of r possible here, which is 3. 1, 2, 3. Because my smallest value possible for cosine of theta was negative 1, and I'm minusing 2 times that. Okay, now I'm going to keep going, but I'm going to kind of go a little bit faster here, because what's happening is I know that cosine is going to be symmetric about this axis, because I get the same kind of values in the third quadrant that I got in the second quadrant. And if I plug in the 2 pi thirds for the third quadrant, which would be 4 pi thirds, then I get a cosine of the same exact value, which was 1 minus 2 times negative a half, or 1 plus 1 of 2. So this is going to be 2. And then if I do 3 pi halves, I get back to 1. So these are coming back down like this. Now I'm going to try 4 pi, not 4 pi thirds, but 60 degrees in the fourth quadrant, which would be 5 pi thirds. So 60 degrees in the fourth quadrant and 5 pi thirds. Now I get a positive. I'm back up to what this value was. I'm back up to 0. And then when I go back to 2 pi, I'm going to come back here to this 0. And so my answer for this graph is this curve. It's called a limicon with an inner loop. And that's the graph of it. And some of this, I did literally just plot points. You were there with me while I was plotting these points, and I did get these points. But I also understand a little bit of how the points should be connected. And so that's how I was able to connect them so easily. Once you do more practice with them, you'll understand how they should connect and the kinds of pictures they should form. But I'm still plotting the points to figure out which ones of the pictures it is. Okay, let's do another one. This is r equals 4 sine of 2 theta. So we're going to do theta and r. Let's again start with theta equals 0. Now the sign of 0 is 0, and 4 times 0 is 0. So I'm right there on the origin. Let's now move, since this is 2 times theta, if I would like to take the sine of 30 degrees, which I would because that's a half, then I need to do half of 30 degrees, which is pi 12. So I'm going to plug in this really small angle, pi 12. Then I get for r 4 sine of pi 6, which is 4 times a half, or 2. So at pi 12, I get 2. Now let's move on. Let's try to get pi halves in there, because I know that the sign of pi halves is 1. So in order to get pi halves, since I'm multiplying by 2, I have to start with pi fourths. So if you see if theta is pi fourths, then r is 4 times the sine of pi halves. Sine of pi halves is 1, so r is 4. Here. So at pi fourths, I get 4, all the way out to here. And I'm going to connect these with a curve. Now let's go and do, let's try to get to 30 degrees in the second quadrant, which would be 5 pi 6. But I'm going to have to try 5 pi 12 instead, because I have to multiply by 2 when I plug in theta. So now I get 4 times the sine of 5 pi 6. 5 pi 6 has a sign of positive 1/2 because that's in quadrant 2, even though my 5 pi 12, which is my theta here, is in quadrant 1. So I get back to a positive 1/2, so this is 2. So I came back down. All right, and now I'm going to do pi. Pi halves. So now I'm going to try pi halves, 90 degrees. If I plug in pi halves, I get 4 times the sine of 2 times pi halves, 4 times the sine of pi. That's 0. So I came back to 0. Okay? So this is actually, it looks like a flower petal, and that's what it's called. It's called a petal. We have to keep going, though. We've only done the angles between 0 and pi halves. I'm going to try to go a little bit quicker now. I'm going to not do these pi 12s in between. So let's do 3 pi fourths. If I do 3 pi fourths, I end up plugging, when I plug 3 pi fourths into theta, I do 4 times the sine of 3 pi halves. Well, 3 pi halves gives me -1, and so this is a value of -4. And in fact, all of these second angle quadrant angles, once I multiply them by 2, they're going to stick me into the bottom part into the third and fourth quadrants, which gives me negative values. So at 3 pi fourths, this big red line here, at this angle, I need to go backwards 4. And what would have happened is I would have gotten, when I plug in, because I was here at 0, right? So then when I plug in pi, so this angle here, pi, this negative x-axis, then I get 4 times the sine of 2 pi, which is 0. And so I came back to 0. Now I'm going to try pi fourths in the third quadrant, which is 5 pi fourths. Once I plug 5 pi fourths into theta, I get 4 times the sine of 5 pi halves. 5 pi halves is up here where pi halves is. They're coterminal, and the sign of that is positive 1. And so I get a radius of 4 again. And so what's going to happen here is, remember, I came back to the origin. I'm going to come back out to this big maximum value and then back in. And then because at 3 pi halves, if I plug 3 pi halves in for theta, I take the sine, I get 4 times the sine of 3 pi, which is 0. And so I get back to 0. So my last value that I'm going to try for getting this maximum pi fourths is 7 pi fourths. So when I plug 7 pi fourths in, I get 4 times the sine of 7 pi halves. 7 pi halves is coterminal with 3 pi halves, which gives the sign of negative 1, and so I get a radius of negative 4 again. This is 7 pi fourths. I have a radius of negative 4, so that's back here in quadrant 2. And remember, I was just in quadrant 3, and I came back here, and I got this. All right, so let me show you in bright yellow here the order in which this was plotted. So when I started with angles in quadrant 1, I actually plotted this petal here. Then I came back down, and when I did angles in quadrant 2, I got negative values, and that took me here to quadrant 4. Okay, so when I stop right here, I've gotten just to pi. So right now, this yellow portion of the graph was plotted when I graphed values between 0 and pi. Now, as I go beyond pi to from pi to 3 pi halves, I actually stay within the quadrant in which I'm plotting. And then finally, in the fourth quadrant, I came back here. I got negative r values, so I came back and traced out quadrant 2. And I'm back to where I started. So this is a rose curve, and it has 4 petals. Okay. Now, the next thing I would like you, so those are all of the graphing we're going to do by hand today. And you're probably going to think that that was pretty challenging. There was a lot of trig to remember when we did those. So there are special polar graphs, and they are all listed on page 790 in your book. And there are 3 major types. The first type is limicons, and we graphed one of those. And there are 4 subspecialties of limicons. There's the limicon with the inner loop, which is the one that we did, a cardioid, which looks like a heart, and a dimpled limicon, which looks like a heart but it's not pointy enough, and a convex limicon, which really looks mostly like a circle but it's not. And those are all based on the graphs on that page, and they'll tell you when you have one or another. So what I'd like you to do here is go to page 790 in your book and draw out those 4 types of limicons and give me an example function for each one. Okay, they do it very specifically with like a's and b's, and if a over b is greater than 1, then it's this one. But just give me an actual example for each one. Then the next type are the rose curves, and we did one of those as well. Those are petals. In the rose curves, you have either an odd number of petals or an even number of petals, and it's all based on what the number is in front of the theta, and you can look all of that up. Again, they have 4 examples there, and I'd like you to draw 4 curves with 4 examples. So we're going to go to page 790 in the book and draw example graphs. And then finally, there are circles and lemniscates. Circles and lemniscates. And these are the ones that I actually do have memorized. These ones I don't bother to plot because they're very simple. And so I will go through and show you these 4 types of examples. And so the first type is a circle on the x-axis. And this is what you get if you have r equals something, say 4, times the cosine of theta. Okay? If this is 4, then the diameter of your circle is 4. It's whatever that value is. Okay? Now, if you have instead something like r equals 2 sine theta, then you're going to be on the y-axis, and your diameter will be 2. If you have r equals negative 2 sine theta, then that's going to be on the y-axis, but in the negative part of the y-axis. Okay, and then those 2 circles I do have memorized. The lemniscates I actually don't know, but I'll write these down for you also. This is where you have r squared equals a squared sine 2 theta. And for the y's, this lemniscate looks like an infinity sign in the first and third quadrants, almost like a petal, and but it's not a point at the end, and this value here is a. And the other one is r squared equals a squared cosine 2 theta, and this is an infinity sign that stays on the x-axis, again with an infinity length of a. Okay, and so last 2 examples. Sketch these graphs. I'm going to show you these without plotting points. The first one is r equals 3, and this is very simple. Notice there is no theta value. And so that means if theta is 0 or pi halves or pi or 3 pi halves, it does not matter because the radius is always 3. You always go out 3 at whatever angle you have. Any angle you have, you're supposed to go out 3. So this just makes a circle of radius 3, centered at the origin. And then this one, r squared equals 9 cosine 2 theta. I don't know if you remember this, but this is a lemniscate. And it's cosine, so we're going to be an infinity sign along the x-axis. And this value right here will be 3, because this was your a squared. And so there's something to be said for memorizing the types of graphs, because it's obviously way faster to graph them, but you do have to memorize. All right, and that's all for this section.